even more, and we said, okay, well, what if we graph like a linear function over a linear function? So ax plus b over cx plus d. And that was all pretty straightforward. These last ones that we did yesterday, there was some different rules to find the asymptotes. Today, it's just crazy. So today, we're going to talk about graphing polynomials over another polynomial. So think back to like chapter 1 and 2, where we have like x to the second, x to the third, x to the fourth. It's going to be those ones. So let p of x and q of x be polynomials with no common factors other than plus or minus 1. It just means that if you factor them, they don't have like the same factors that would just cancel out. The graph of the following rational function has the characteristics listed below. So they give us this really weird, you might remember this general polynomial function from chapter 2 that nobody, you just have a panic attack when you read it. The important thing here is just note that you have an m degree on top, so it's your highest degree is m, and on the bottom your highest degree is n. And that's going to help us remember. Alright, then they give us some facts about these rational functions. The first one is that the x-intercepts of the graph of f are the real zeros of the p of x. Okay, super cool piece of information. It is true, and I'm never going to answer that question. Okay, so number 1 is kind of a throwaway. I'm not going to focus on it in this class. It is true, but we're not going to worry about it. Number 2, the graph of f has a vertical asymptote at each real zero of q of x. This is super important. This is one of the things we're going to deal with. So our vertical asymptotes, it's not like some formula you can do like in the last section. It's where we're going to have to factor the denominator. So factor denominator. Those are going to be our vertical asymptotes. And then number 3, the graph of f has at most one horizontal asymptote, which is determined by the degrees m and n of p of x and q of x. So number 3 is sort of this whole box. Because it gives us our 3 cases. And it looks kind of overwhelming, but today we're just going to focus on the first case, where if your degree of your numerator is smaller than the degree of the denominator, your horizontal asymptote is automatically at y equals 0. So that's going to be true for everything we do today. We're just doing these. So let's look at example 1 together. We're going to graph the rational function again where m is less than n. We're going to state the domain, range, and equations of the asymptotes. So our first step here is our horizontal asymptote. At most, it's going to be 1. And like I said today, it's going to be the same thing. So notice the degree in the top of our function here is 0. That's because there is no degree, right? There is no power. It'd be x to the 0, but we would never write that. And then our n, highest degree at the bottom is 2. So, just a quick check here. This means that your m is less than your n. That's true. So, your horizontal asymptote is at y equals 0. Remember that? That's going to be true for every single one today. The second step, our trickier step, we need to find our vertical asymptote or asymptotes. So vertical asymptote. So this is where we have to factor that bottom part. So our bottom part is x squared plus 1. And we would set it equal to 0 because that solving for x and less is find that vertical asymptote. All right. If nothing, right?
Yeah.
If it's going to add to 0, one has to be negative, one has to be positive, and the negative times the positive will be the negative, so this just doesn't work. So it does not factor, which is kind of good news for us, because that means it has no vertical asymptotes. Does not factor, meaning no vertical asymptotes. So we just have the one asymptote from here. It's basically the same as what we did the past 2 days. We're going to start by graphing our asymptotes. We only have the one that's at y equals 0. This is the line that we cannot cross. And now we're going to go to our calculator. I'm not going to show you the calculator app. I'm going to trust that you all have your calculators and you can graph these points. When you graph this in your calculator, you're going to have to put the bottom in parentheses. So when you type this, it should be 6 divided by parentheses x squared plus 1. And you'll get a table of values. 6 divided by parentheses x squared plus 1, second table. Okay, so again, unlike yesterday, I can't tell you, hey, center around the error, graph 6 total points. I can't tell you how many points to graph because these are all going to be different. What I choose to do is I try and find easy to graph points. You're going to at most graph 10 and that is 20 points, right? And so it goes from negative 10 to 10. Did you ever graph 20 points? Heavens no, please don't. But, you know, that's a range of values that you could possibly graph. I try and graph whole numbers. I try and find some symmetry. So if you're looking at the table, you should notice that there's some symmetry around 0, 6. Right? Because at negative 1 is at 3 and at positive 1 is at 3. At negative 2 it's at 1.2, at positive 2 it's at 1.2. Those are the values I try and find. Again, I can't give you a minimum. I can't say, graph 6 points. Graph enough points that you get a nice looking graph. I should see some points. I don't want to just see, a crazy shape. I need to see some points. So 0, 6. Like I said, there's symmetry around this. So at negative 1 it's at 3. At positive 1 is at 3. At negative 2 is at 1.2. And at positive 2 is at 1.2. And then at negative 3 it's at 0.6. And at positive 3 is at 0.6. These will never just be like straight lines. Like I don't want you to make it look like a star or anything, right? It's got to have some curve to it. Just as I'm going to cross that x, or that asymptote. Okay, so the really tricky part of today is going to be the domain and range. Because again, you can't just plug and chug mindlessly here. You really have to understand this interval notation at this point. We've done it a lot, so hopefully it shouldn't be too much of a burden. Your domain here, we're thinking of all the values of x that this function runs through. It runs through everything. There are no asymptotes. It goes through everything. So that means our domain is negative infinity up to positive infinity. Our range, so our range is our y values. It starts with the asymptote, but remember it doesn't include it. And it runs all the way up to this point up here. It does include that point. It stops there, but it includes it. So we start at the asymptote, which is 0, and we run all the way up to 6, right? This is at 0, 6. However, 6 is included, so you have to have a bracket on it. The only time you don't have a bracket on the numbers is if it's an asymptote or if it's an infinity sign. If it is included, it needs to have a bracket. So our domain was negative infinity to infinity. Our range is from 0 up to 6, including 6. Questions about this one? All right, let's ramp it up. we gotta change part B, bonding one to actually factors. So erase the bottom part, not all of it. Make it x squared minus 4. I want to make sure I include one that actually does that. So we have y equals 4 divided by x squared minus 4. So again, we're going to start out with that horizontal asymptote, and today they're always going to be the same. So a horizontal asymptote. And this is going to be, so your n here is 0. Your n is 2. Your n is almost always going to be 2, because if I'm asking you to factor the bottom, I don't really want to give you like a cubed or a fourth power or a fifth power. There is one on the homework that's a third power, but it's actually really easy. So our n here is less than our n, that is true, 0 is less than 2, which means that we have a single asymptote, horizontal asymptote at y equals 0. Our vertical asymptotes, here's the fun. So we have to factor the bottom. So the bottom is x squared minus 4. You could factor this, or actually you could just solve this using square roots. Either way, I'm going to factor it. So this is the same as x squared plus 0x minus 4. Well, what multiplies to negative 4 but adds to 0? What multiplies to negative 4 but adds to 0?
Negative 2 and 2.
Negative 2 and 2. So we have x plus 2, x minus 2 equals 0. If you set each of these equal to 0 separately, you'll get x equals negative 2 and x equals positive 2. And I'm making sure to show this step right here. I know probably you don't need that, but I just want to remind you that you have to set equals to 0 because officially their signs are changing, right? Sometimes we forget that when it's the same number with different signs. So we have two vertical asymptotes. We have one at x equals negative 2 and one at x equals positive 2. So this function looks crazy. Yeah, you can. Just remember to graph it. Yeah, the question was, could you write x equals plus or minus 2? Yes, of course. Just make sure you graph it. So we have an asymptote at y equals 0. We have an asymptote at x equals negative 2, and we have an asymptote at x equals positive 2. So our points, again, go to your graphing calculator. When you type this in, you're going to want to type this in as 4 divided by parenthesis x squared minus 4 close parenthesis. The second table. Notice you have 2 errors. So you have 2 vertical asymptotes. So you're going to want to graph around those errors. I think I graphed from negative 4 to positive 4. So starting at negative 4. At negative 4, we're at 0.3. Go over to the left 4, up 0.3. At negative 3, we're at 0.8. And then at negative 2, there's an error, right? Is that correct? At negative 1, we're at negative 1.3. At 0, we're at negative 1. And then at 1, we're at 1. unions in our domain. So it's really small. So for our domain here, to start, we start at negative infinity all the way up to this first asymptote at -2. So we go from negative infinity up to -2. Again, it's not included. Then this middle part, we go from -2 up to +2. So we have a union, -2 up to +2. And then finally we go from +2 up to positive infinity. So another union, +2 up to infinity. Pretty good. Now I actually think the ranges are trickier here. And that's because it's mixing two scales that we've used for ranges. So we're going to start at infinity, negative infinity rather. And we go all the way up to this top point right here. But that top point is included. So we go from negative infinity up to that top point is at -1. However, -1 is actually the point on our graph, so it's a graph. Then there's a pause. There's nothing in between the two, and we start up again after our asymptote all the way up to infinity. So we have a union here. Our asymptote's at 0 up to positive infinity. Like I said, there's not some quick and easy trick for these. It's just, it takes really understanding these domain ranges. It might be that this actually helps you understand the domain range better because it really is chopped up. So it's going to have multiple pieces to it, so it really forces you to kind of run through it. Any questions? Sorry, go ahead.
Is there supposed to be a bracket on 0?
No, because it's an asymptote. It's not actually a specific point, right? We don't have a specific point at 0.
Okay.
Okay, so one weird thing I want to warn you about is we have at least one problem where actually the inside looks just like this, except for on the inside, the function goes like this. That range, it actually moves through the asymptote, even though it's not technically, I mean, it's an asymptote, right? It's not supposed to. That can happen. If that happens, the range is actually -3. And one of your problems with that. I'll talk about that towards the end. So, you guys can get started on your homework. My Zoom people are going to stay on because the last 5 minutes, I'm going to see if there's any questions. I know there's at least 2 problems that I kind of want to go over from today.